This directed graph represents a network of pipelines along which oil can be sent. The goal is to ship as much oil as possible from the source S to the sink T. Each pipeline has a maximum capacity it can handle. 2 units of oil can be sent from S to T by going from S to A to D, and D to T. Notice that the amount of oil going into each node is equal to the amount of oil going out of it. 1 unit of oil can be sent from S to C by going from S to B, B to D, and D to C. And 4 units of oil can be sent from S to C. Hence, 5 units of oil can be sent from C to T by going from C to E and E to T. This flow from S to T ships 7 units of oil in total. A flow network is a directed graph that has a source node S and a sink node T, where each edge is assigned a non-negative capacity. The flow through each edge must be non-negative and less than or equal to the capacity of the edge. For all nodes U except S and T, the amount of flow entering U equals the amount leaving U, meaning that flow is conserved. The size of a flow is the total quantity sent from S to T, and by the conservation principle, it is equal to the quantity leaving the source S. Before we dive into the algorithm for finding the max flow, it is essential to understand what a residual network is. A residual network is derived from the original flow network G and includes the same vertices. For each edge, U, V, and G, the residual network includes a forward edge UV with residual capacity equal to the capacity of the edge minus the flow if the flow is less than the capacity, and a backward edge VU with residual capacity equal to the flow if the flow is positive. The Ford-Fulkerson algorithm finds the max flow of a network. First, we initialize the flow of each edge in the graph to be 0. A path from S to T in the residual network is called an augmenting path. While there exists an augmenting path in the residual network, we find the minimum capacity of the edges in the path, and for each edge, UV in the path. If it's in the original graph, then we increase the flow of UV by this amount. Otherwise, if it's not in the original graph, it must be a backward edge, meaning that VU is an edge in the original graph, and we decrease the flow of VU by this amount. This is because increasing the flow in the backward direction is equivalent to decreasing the flow in the original direction. When the residual network no longer has an augmenting path, the network is at maximum flow, and we return the flow. Here's an example of running Ford-Fulkerson's algorithm on the graph from the beginning of this video. The flow of each edge is initialized to 0, so the residual graph is the original graph. We begin by finding an augmenting path. The minimum capacity of the edges in this path is 1. Thus, we increase the flow of each edge in the path by 1. Since the flow of these edges have changed, we need to update the residual graph. Since the capacity of edge SA is 3 and the flow is 1, we create a forward edge with residual capacity 2 and a backward edge with residual capacity 1. For edge AD, we create a forward edge with residual capacity 1 and a backward edge with residual capacity 1. For edge DC, the capacity is equal to the flow, so we do not include a forward edge, and we create a backward edge with capacity 1. Since the capacity of edge CE is 5, we create a forward edge of residual capacity 4 and a backward edge of residual capacity 1. The same holds for edge ET. We repeat this process by finding another augmenting path, increasing the flow along the edges of this path, and updating the residual graph. Now notice that edge ED of the augmenting path is a backward edge. Thus, instead of increasing the flow of edge DE by 1, we decrease its flow by 1, so the flow of DE is now 0. At this point, the residual network no longer has an augmenting path, which means the network is at maximum flow. The maximum flow is 7. The max flow min-cut theorem states that the size of the maximum flow in a network equals the capacity of the smallest ST cut. In our example network, If we partition the vertices into a set containing S, A, and B, and another set containing T, D, E, and C, then the sum of the capacities of the edges that connect the set containing S to the set containing T is 7, which is the maximum flow in this network. Since the flow cannot exceed the capacity of the smallest cut, and it is possible to achieve a flow equal to this capacity, the maximum flow must be equal to the capacity of the smallest ST cut.